Okay, hello everybody. I hope that you are doing well. I want to welcome you to freemathhelp.ca and thank you for joining us. We are now moving into the grade 11 hours, so if you are joining us, we are going to be focusing on grade 11 work. And sorry, I was just fixing my sound there. And basically, if you aren't in grade 11 and you are joining us and you're from any other grade, 9, 10, or 12, there are specific hours dedicated to each grade, so feel free to join us in next week's hour for your grade if that would be helpful for you. So for those who might have been tuning in last week, we started out our trigonometry learning, and the reason that we focused on this so quickly in the Free Math Help trajectory is because it really is one of the most important units. It does carry on into grade 12. And if you do find yourself not focusing on all of the main aspects of this unit in grade 11, it's going to make your grade 12 learning very difficult. So that's why we're trying to make it as easy as possible and just have a good understanding of all of the different rules. So before we get started, I also want to mention that if you do have questions from your class that your teacher has assigned for distance learning, then please feel free to message them to us in the chat, or you can email them to us at admin@scholarlyelite.com. We will be happy to address those if it's something that is in the grade 11 curriculum. So I'll just put that thing there. Okay. Awesome, guys. So let's get started. Now, last week we were talking about, how the Cartesian plane that we're used to seeing relates to something called the unit circle. And the unit circle realistically is something that pertains specifically to trigonometry and that we are going to refer to on many different occasions. So if we recall, we know that a circle in general has 360 degrees. So if we're looking here at this Cartesian plane and we look at the various quadrants, we've got quadrant 1 chilling over here, quadrant 2, quadrant 3. And if you're not familiar with the quadrant numbers, it's really good to practice that and just to make sure that you are aware of which quadrant is which. So we've got our 4 quadrants here. And in each quadrant, obviously, you have a certain number of degrees that pertain to that quadrant. So from here to here, it's 90 degrees. So this point here is 90. Then from there to there is another 90 degrees, and that's going to make this point here 180. Keep on going. We've got 270 degrees, and last but not least, we've got 360. Okay, and if ever you guys are like in a rush and you're not 100% sure of what this third one is, just think 90, and then this is 8, 7, 6. It's easier to remember that way. Anyways. Okay, so today we're going to talk about a couple things. Last week we started discussing, the initial arm, the terminal arm, what that all means, and all of that fun stuff. But today we're going to actually start applying that knowledge and using it in a way that's actually helpful for us. So I'm just going to erase these really quickly. And as I always say, if you have any questions along the way, please feel free to stop me. I'm happy to go back and explain things again and just make your lives generally as easy as humanly possible. So, okay. First things first, I just want to reiterate what the initial arm and the terminal arm are. So for any angle, you have your initial arm, which is the starting point. So if you're picturing a protractor, that's like the base of the protractor. And then the next part is the terminal arm, which means the final part of the angle. And then basically the difference, or the distance kind of, not the distance, but the degree, the difference in degrees between these two things gives us the angle, which we also refer to as theta. You're going to hear that word a lot in math. So we've got that. Okay, guys? So keeping that in mind, if we're looking over here at our Cartesian plane and trying to understand what this all means, we've got a couple different terms that we really need to have down pat as we're going into doing different assignments and stuff. So if you've got your standard position angles are angles that range from 0 degrees to 360 degrees. So that's the range, 0 to 360. Okay, so basically any angle that's within 0 to 360 degrees, that can be referred to as a standard angle. So if I'm looking here and I'm trying to make this so that you guys can actually see it, so we've got this as our initial arm, and then let's say that our terminal arm is over here. Okay, and we're taking a look here, and we know now that we're going to need to solve an angle for this, and it's obviously an obtuse angle because it's more than 90 degrees. So we've got from here to here, which is 90, like I said earlier, plus another 90. And let's say arbitrarily that from here to here, we've got, I don't know, another 30 degrees. That's actually not a good example. Let's say 45 degrees because it's basically in the middle. So altogether, I know that this angle is 225 degrees, right? All the way around. That's 225. So what we're going to talk about today are a couple other things that really come into play when all of this is involved. So there are 3 terms that we're going to learn today that are very important for you to remember. So I highly recommend writing them down, okay guys? We've got the principal angle, and this is the smallest possible angle. I'm just going to use theta for angle, okay guys? That is positive. So I'm going to put here positive. Whoa, my pen, there we go. Coterminal with a given angle. So we're also going to discuss what the heck coterminal means. So coterminal angles have the exact same, basically their same ending spot, okay? And what that means is essentially, for example, 225, this angle ends up over here, right? Right where we were looking earlier if you take a look here. But we can also go backwards and create another angle this way. So this is 90 plus another 45 here. And that would make this angle negative 135 degrees. So 225 and negative 135 are both coterminal angles because their terminal ray ends in the same spot. Okay? And it's important that you remember what that means. So coterminal, I'm just going to write it as look the same. It doesn't mean that they are the same. They just look the same. Terminal ray ends at same location. Hope you guys can read my writing. Okay guys, so we've got our coterminal angles, thetas, and then we also have reference angles. So reference angles are basically angles between (0 degrees and 90 degrees that essentially tell us what the cosine and sine are going to be. So that are related to the angle in question. And I hope you guys can hear me okay. So I'm going to do a little bit of erasing here just so that we can come back and understand everything separately. Whoa, what am I doing? Here we go. Okay, so we know that I drew this angle to be 225 degrees. Sorry, I'm trying not to get rid of our awesome stuff here. Eventually I'll draw this again, but anyways, okay. So let's talk about each of these things separately. Okay guys, so let's talk about coterminal angles first. Like I said, coterminal angles, you've got 225, which is this angle here, and one of its coterminal angles would be negative 135. But there are other ways to solve for a coterminal angle. So for example, let's use an example like this. So if we had 360 degrees all the way around, pretend that this is all connected, and then I keep going and I add another 225 degrees to 360. So that'll be 360 plus 225. So 585 is another coterminal angle. So we've got 225, we've got negative 135. These are all coterminal angles because they're all chilling in the same spot, looking exactly the same. Okay, guys? This is an important thing to understand because you're going to get questions where the teacher's going to ask, okay, well, what are the coterminal angles? Cool. And then they're going to ask you, what are the cosine and sine? Well, if you know the cosine and sine of your original angle, then it doesn't matter because you've already got the answer to your coterminal angles, cosine and sine, because it's the same, because it's in the same exact quadrant. It's in the same exact spot. Okay, guys, so that's really important to remember. Now, this is going to be a little bit different when we're talking about reference angles. So let me just do some erasing again. So I hope that makes sense. If it doesn't make sense for you guys, just feel free to let me know. Again, I'm always happy to go over stuff. And if you guys have been in the chat before, you know that we also allow questions that don't have anything to do with the lesson. So if you do have questions from your class, you're welcome to send them in. Okay, so let's talk about reference angles. So the word reference kind of gives away what this means. We're using this as a reference so that we can make things easier for ourselves, okay? So when we talk about reference angles, we're always referring to the x-axis, okay? So keep that in mind. It's really important, okay? So the reason we are goes like this. So we know that this angle altogether, we've been chatting about it this whole time, 225 degrees altogether. Okay, guys? So when we're talking about a reference angle, oh, that's bad. Let me fix that. Talking about a reference angle, what we're really asking is what angle in the first quadrant is equal to the distance between the angle that I have and the x-axis from where it is. So I'm going to explain that a little bit better, okay? So from here to here in the angle 225 degrees, because the angle 225 goes all the way like this, right? But realistically, from where the x-axis is to where the angle is, it's 45 degrees of a difference. Well, that means that the reference angle for this particular angle is also 45 degrees. So the way that you're going to solve reference angles is by asking yourself, what's the distance between my angle in the quadrant where it is and the x-axis? Okay, and we're going to do some other examples as well. So I've just been using 225 to keep things consistent, but again, we're going to do some other examples so that you have a good reference, no pun intended, for what we're learning right now. Okay, guys? So why is it important for us to understand reference angles? Well, reference angles, A, make it really easy for you to understand what the cosine and sine are going to be for your more complex angles like 225, like 585, like negative 135, right? Because it's going to tell us a couple things. So if anyone was with us last week, you'll remember that the sine and cosine go like this. We go cosine is x and sine is y. And the way to remember that, or at least the way I remember that, is that they're alphabetical. Cosine goes first, sine goes second, okay? And if I know what the cosine and sine are of my particular thingamabob, angle is what I'm trying to say. I'm trying to pull up a unit circle here, so just bear with me for 1 second while I find my unit circle that I printed out special for this occasion. Perfect. Got it. We good. We good. We got it. Okay. So if we're looking at the unit circle, we know the cosine and sine for the angle 45. And this is something really important that I actually highly recommend you guys memorize. Like I was saying last week, there are two standard triangles that I really recommend you memorize, because once you've memorized those two triangles, you've actually memorized the entire unit circle in actuality. So it makes your life a lot easier. But we're going to save ourselves a little bit of time and just go ahead and get that answer. So we know that the cosine of 45 degrees is equal to root 2 over 2, and the sine of 45 degrees is equal to root 2 over 2 as well. Okay, so now for those of us that were here last week, we remember that the cosine and sine xy paradigm, we'll call it, pertains to the Cartesian plane. So again, you know that in the Cartesian plane, this quadrant 1 has x positive, y positive. Quadrant 2 has x negative, y positive, and so on and so forth. Negative, negative, and positive, negative. It's really important to keep in mind, and again, that's how these things relate to one another. So cosine, sine, x, y, and that way you can remember what's positive where. Some teachers use CAS rule as well. It really just depends on what you prefer. I think that CAS rule is a gross oversimplification of what's really happening, and it doesn't really help you guys understand what's going on a more granular level, on a real deep level that you're going to need to understand for next year. So that's why I highly recommend memorizing it this way, just like a normal Cartesian plane, and using that knowledge and applying it, okay? So back to what I was saying earlier, our reference angle, which is 45 degrees, has the following situation for its cos and its sine. Now in this case, both cosine and sine are both positive because the reference angle is in quadrant 1, okay guys? It's important that when you're using your reference angle to determine the cosine and sine of the angle that you're discussing, which is your standard position angle, 225, that you remember what the quadrant tells you. So in this quadrant, we know that cosine is negative and sine is negative. So in that case, the cosine of 225 is going to be negative root 2 over 2, and the sine of 225 is going to be negative root 2 over 2. Okay guys, I hope that that makes sense for you. If it doesn't, like I said, just feel free to let me know and I can go over anything that might be confusing. I know that this is a lot of stuff thrown at you guys all at once, but the reason I teach it this way is because I actually, in my years of tutoring, was always confused as to why teachers taught these concepts separately and then expected you guys to mesh them all together, when in fact they're really all quite related as concepts, and whenever I teach them to students all together, people seem to understand them better, okay? Now, whenever I have taught them, because I personally don't tutor anymore, even though I do miss it. But yeah, so there's this. Okay, guys? So I hope that that makes sense for you guys. We're going to do another example just to make sure that it's more clear. But if you do want to go over anything, we absolutely can. Okay, guys? Let's take a look here. So let's just do some erasing. Erasing it. There we go. Oh, this Cartesian plane has seen better days. We know. We definitely know. But we're doing our best here. I want to keep all this stuff that we wrote already, which is why I'm not going to a new page. So I'm sorry guys about that. Okay, so let's do this. Let's just do a new color. See how that goes. Let's amp it up a little bit. Let's make it, no, not red. We're using red already. Let's use this. Let's use purple. Okay. Oh, look at that guy. Killing it. Wonderful. Okay, so let's do another example here. So let's take a look at, let me just pick one. Sorry, I'm just going to pick one that makes sense for you guys. So we're going to draw the angle 590. So let's take a look here. 230. Okay, so for the angle 590, I'm going to illustrate to you. Oh my gosh, why does it do that? There we go. So I'm going to show you guys what's happening when we draw the angle 590. Okay, So it means we're going all the way around to 360. And then we're also adding another 230, which would be somewhere around here. So let me just get that real quick. 590, 230, so. Okay, so it's pretty close to where we just were. Okay, guys, so we're going to show that. There we go. Now, let's start this from square one. All right, guys. So our angle here, this is angle. I'm going to fix that so it's not as intense. There we go. This is angle 590. Okay, guys. So let's go piece by piece here and just talk about the different things that your teachers are going to expect of you on exams and stuff. So first of all, they're going to ask you, what is coterminal with the angle 590? Well, we know that coterminal angles literally look the same, meaning they're in that same spot. Well, there's a couple different ways that you can solve this, and everybody has their easiest way to do things. I'm the kind of person that I like to do things piece by piece. That's just how my brain works. But if you're a person who likes to be 10 steps ahead, more power to you. So for the angle 590, what I first want to ask myself is, how did I get here? Well, this is 360 degrees plus an extra 230. Okay, so that means from here to here, let me put it in a different color. This is an extra 230 degrees, which actually means that the angle 230 is also coterminal with 590. Okay, guys? Now, another thing that we can do is say to ourselves, well, on top of that, we could go another full rotation. So we could say, like, for example, 1, 2, so now we're at 720, and then add another 230 to 720, which is 950. So here we have 3 coterminal angles. Chillin' like villains. What does that mean? All of these angles have same sine and cosine. Okay, guys. Well, now let's make finding that sine and cosine a lot easier, okay? So, how do we solve for our reference angles? This is something where it's really, it seems really simple when you're watching someone else do it, but it does involve paying attention really closely and practicing these yourself, because it's really easy to get these confused, okay? So remember, reference angles, they are always between 0 and 90 degrees, and we always solve for them using the x-axis, okay? So when we're solving for this particular one, I'm going to say to myself, well, I know that the most, simplified version of this is 230 degrees, okay? Even though we're really talking about 590, but in this case, I'm going to use 230 because that's easier. And I'm going to say to myself, okay, well, what's 230 degrees minus 180 degrees? Because that's how I'm going to solve for this distance, for this angle, I mean. Okay, guys? So I hope that makes sense. If you're confused by anything, like I said, just let me know and we can go over it again. So here we go. We can solve for that. So 230 minus 180, and I'm going to get 50 degrees. Okay, why is that the case? Why am I using the number 180? Well, if you think about it, from here to here, running out of space here, but from here to here, that's 180 degrees. Well, what's the leftover? 50. Okay, guys? So 50 is now my reference angle. Reference angle is 50 degrees. And then I'm going to go ahead and solve for the cosine of 50 degrees. So 50 degrees has a cosine of 0.64. It's not one of our standard angles, so it's not something we would have just off the top of our heads, but that's okay. And then the sine of 50 degrees is 0.76. Okay, guys, so that means that here the sine and cosine of 590 degrees is going to be negative 0.64 is sine, and cosine, oh, sorry, that's cosine. This is sine. And that's going to be, hopefully you guys can see through my chicken scratch, but basically this is going to be negative 0.76. Okay, guys, so again, I'm not going to belabor this point too much. We don't need to go over this a million times because I think that you're all smart kids and you do seem to understand everything. But like I said, just because we're zipping through things does not mean that we cannot go back and explain stuff again. Okay, so I'm happy to answer any questions you guys have. I don't want you guys to feel like, I know a lot of kids in class, they feel like they don't want to ask questions because they don't want to put their hand up in front of everybody. This is why I like this platform, because it allows us to ask questions without having to talk in front of everybody else. Okay, I'm just going to full on erase this at this point, or I'm going to create a new one so that we can do some other example. Now, keep in mind that when we're doing questions like this, it's very easy for things to get complicated very quickly. So it's good that you try to understand all the specific little pieces of each thing. Okay, guys? So moving on, let's talk about something a little bit different. Let's look at some negative angles. Okay? Now, if we're talking about negative angles, those are angles that start here, start at the x-axis, and go counterclockwise. Or no, sorry. Yeah, go clockwise is what I meant to say. They go clockwise instead of counterclockwise like most angles do. So let's take a look here. Let's put an angle. And if we're looking at, let's see here, negative 740. So we're talking about, oh, what am I doing? There we go. Doing this and making this a little bit bigger. So here's our initial ray, initial arm, right? It should start at 0, 0. it's hard to do on this thing. There we go. There's the initial ray. And then we're going to talk about how we get to negative 720. So let's take a look here. Sorry, not negative 720, negative 740. So again, when we're looking at negative angles, we go this way. So we go one rotation around, that's 360. The second rotation around is 720. And then 20 degrees downwards. Something like that. It should look around there somewhere. Okay, guys, so this angle is negative. Oh, I don't want it to be that intense. Let's just fix this quickly. Perfecto. Okay, so this is both our standard, not standard angle, sorry. But this is the angle that we're discussing. But then here, this seems just way too small now. There we go. Should be something like, there we go. Okay. So again, how did we get this? Well, we went around 2 times. So if we're saying we're going this way, there's 360 and there's 720, and then we added an extra 20. So first, let's talk about what is a coterminal angle. And if you're following along, we know that coterminal angles always look the same. They're in that same quadrant. They're in the same spot. So negative 20 is also a coterminal angle. And if we were going the other way, this way, we would say to ourselves, okay, well, what's this angle? Well, I could say, well, what's 360 minus 20? 340. That's also a coterminal angle. Okay, guys? Now let's talk about our reference angle. What is a reference angle for this? Well, if we think about it, 20 degrees would also be a reference angle. So something like that. So we're looking here. So 20 degrees, negative 20 degrees, those are the same in terms of their reference. So they have the reference angle is 20 degrees because it's in the first quadrant. And whatever the cosine and sine are, they would be the same numeric value in terms of its absolute value, but they would be different because basically here you have a positive cos, so on this side you have positive cos, positive sine in the first quadrant, and on this side you would have positive cos and negative sine. Okay, so I know that we've kind of gone over this a couple times now in this session, but the reason I have gone over this is because this is one of the topics that kids tend to do the worst in on tests because it seems really logical and they're like, oh yeah, I get it, sure, we're good, and then we get to the tests and people seem to have some issues with it, okay? So it's important that you definitely get this and that things are making a little bit of sense. So what we're going to talk about now is something slightly different, although it is still related on some level. Let's just see if they have a Cartesian plane on here. No, they don't. They have this guy, though, chilling all day. Not necessary. Focus, Arlinda. Get it together. Okay, so here we go. Making the Cartesian plane blue this time. Making it a little bit out of whack there, so let's fix that. Okay, you guys, we're talking about something a little bit different now. So still relating to the unit circle and that particular trigonometry unit that has to do with all of this. But what we are going to talk about are trigonometric ratios of angles in standard position. Okay, so what we're really talking about here are some of the rules and how this all goes together. Okay, guys, so you're going to get a lot of questions that have to do with what we're about to talk about, and it's really not as crazy difficult as it seems. So that's why I kind of want us to go over it so that things can make sense for you guys. Okay, so let me just put that circle in there as well, and we can be on our merry way. So the circle's not going to be perfect. Oh, that's so annoying. Put the circle in last. There we go. So let's pretend that this is a perfect circle, perfectly centered on here. Okay, guys, just bear with me. Technology and I, we're not always friends. But we're getting there. Okay, cool. We got it. We got it. Okay, awesome. Let's just change our color quickly and I will explain what the heck I am trying to show you. Okay, guys, so here we have a point which is denoted by x and y. Okay, you're going to get a lot of questions like this, and I'm going to show you exactly how you can solve them so that it makes your life a lot easier. Okay, so we know that our primary trig ratios are defined in terms of x, y, and r. So what r is a radius. Okay, so here I'm going to pretend like I have a straight line ability, and this is a right angle, as we know. Here we have theta. And this here is our radius. It's the radius of the circle, is what I'm trying to tell you. That's what I'm trying to say, I mean. So we've got our point xy, we've got our radius, and we've got various situations going on. So when we talk about point xy, we're saying this point on the graph takes place at this particular x, which is obviously a line straight down, and then it takes place at this particular y, which you can show as a line straight across. But I'm going to erase that line straight across. That was just to illustrate that, but I don't want to confuse you guys, okay? So, bring this back as R. Alrighty guys, so starting from the bottom right quadrant, which is quadrant 4, this one here, and reading in a counterclockwise direction, the first letters of the trigonometric ratios that are positive are CAST. This is the CAST rule that I was talking to you guys about earlier, okay? Again, you don't need to memorize the CAST rule if you understand how this works in terms of cos and sine and x and y. Okay, guys? So, the trigonometric ratios that are not positive are obviously negative, and that's important to know when we're talking about stuff like this. So, you're going to get questions like the following. If theta is an angle in standard position, which we know means that it's an angle from 0 to 360, with its terminal arm in quadrant 4, and cos of theta is 7/25, determine sine of theta. Teachers love these questions, and if you go to school in Barrie, which I know a lot of our students do, and especially if you go to school at St. Pete's, I've seen many St. Pete's tests that look like this because the teachers at St. Pete's are actually quite intense. They're very good at math, and so they do a lot of pretty intense questions. But that's beyond the point. Let's get to solving this question. Okay, guys? So they've told us a couple of key things. We know, we've been given the fact that this is in quadrant 4, and we know a couple other important facts, right? So let's go over here before we start answering this question, and let's just learn about these different ratios. So we have sine of theta, which we know is opposite over hypotenuse. And in this case, over here, if we're saying this is theta, this right here, this guy chilling, right? If we know this is theta, then let's discuss what's its opposite. Well, its opposite is y, this y distance, and the hypotenuse is the radius. So we're going to show that here as being y over the radius, okay? Let's talk about cos theta. So cos of theta is adjacent over hypotenuse. And in this case, the adjacent arm is right here. It's the x value. So we have x over radius. Cool, because obviously the hypotenuse is still the radius. And then tan of theta is going to be the opposite over the adjacent, as you know. And that is going to be the y, this part here, the y, over the r. Sorry, the y over the x. My bad, guys. Sorry, that's on me. We got this. We're gonna fix it. Here we go. Over x. Cool. So, what does that mean to us in terms of the question we were just looking at? Well, we can apply this logic to the question that we were looking at, because if we know that cos of theta is 7/25, and I take this knowledge from over here where cos of theta is the x value over the radius, well then we've got two very important values that we now know. So we know that x equals 7, and we know that the radius is 25. So given our knowledge of the Pythagorean theorem, we know that because the radius is our hypotenuse, that our Pythagorean theorem should look like this. R squared equals x squared plus y squared. Okay, guys? So if I just plug stuff in here, 25 squared equals 7 squared plus y squared. So 25 squared, I believe, is 4. Whoa, damn. Yeah, 625. So we've got 625. Hopefully you guys can see what I'm writing. Let me just take a look here. Yeah, 625 over this plus y. And we'll solve over here. So 625 minus 49 equals y. Y equals 576. Y squared, sorry, my bad. Again, sorry guys, not to confuse you. Y squared equals 576. And the square root of 576 is 24. Because I squared both the sides. Okay, so now I know that y equals 24. So first of all, I'm going to just kind of arbitrarily put this here. Right? And I know that the radius is 25, point is 7 for the x. So we're going to take this knowledge. We've got y equals 24. We know what x and r are. And then we're going to find sine. So I'm going to come over here, guys, just because there's more space over here. So sine of theta equals, what is it? 24 over 25. But that's not our final answer. It has to be negative because I know that sine values in the fourth quadrant are always negative. Okay? So if you are asked to solve for this angle, you can definitely do so. But are you going to do it using this negative value? Probably not. And that's why we use reference angles. So reference angles give us an idea that we can work with, basically. So the reference angle in this case, I can solve for by just saying, okay, well, let's do sine when it's a reference angle in quadrant 1, and I can go ahead and plug that into my calculator. 24 divided by 25, and then do sine to the negative 1. So theta is sine to the negative 1. And we can solve, and I get the angle to be 73.7 degrees, which I'm just going to round. So that means that my angle here in the fourth quadrant, is either negative 74, which typically teachers don't want you to write it in that format, right? So we're really going to solve this by saying, well, what's 360 minus 74? So that we can solve it in the in the counterclockwise direction, this way. Okay, guys? So that's 286. So basically, you're going to see lots of questions like this. You're going to always be given questions where they basically give you a point and you have to solve for it. Just remember, instead of memorizing all this jargon and garbage over here, all this trigonometry stuff, in math, my #1 suggestion to math students at this higher level like you guys are in is not memorizing stuff. Do not memorize stuff. Instead, have a visceral understanding of what it is that you're doing, and that will actually make your life a lot easier. And the way to do that is through practice. And really, there's no shortcut. You just have to do the labor that is involved in understanding math. But I promise you, a little bit of practice here is actually going to make your life a lot easier in the long run. So again, remember that these trig ratios are not something you necessarily need to memorize if you understand that we're always talking about that first quadrant when we're talking about those trig ratios, and that it's this angle that we're discussing. And as long as you understand that what's the opposite, what's the adjacent, yada, 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 and you know that you're on the Cartesian plane, you're all set. Okay, guys? So if anyone has any questions about that, feel free to respond in the chat. I'm happy to answer them. I know that it can be a little bit difficult when we are doing stuff like this. We're going to do another example of this type of question. So the question is, if point P x -5 is on the terminal arm of angle theta in standard position. So again, standard position means 0 to 360. And I was hoping today to be able to do some trig identities. We might not get a chance to do that. I really want to dedicate a good amount of time to understanding trig identities and to giving you guys some strategies for solving them that aren't really ever discussed in class, because teachers kind of expect people to figure out those strategies. And I actually think that while there is merit in that, I do think that direct instruction is the best way to teach people, and for years have found that most people are actually much better at math than they think they are, and that the way that the school system is set up is just not conducive to how we learn math. But again, who asked me? Nobody. I'm just here talking to myself, basically. So here's our question. If point P, x value unknown, y value -5, is on the terminal arm of angle theta in standard position where r equals 13, remember r means radius, what is the value of tan theta? Okay, girl, we can solve this. This is no problem. You good, girl. Okay, So let's go ahead and solve our little hearts away. So let's talk about what this is all saying. We know that it's an angle in standard position. We want to know the value of tan theta. Let's recall what we know about solving this. So remember, this is y, this is x, this is some random theta, and we can solve for things using these accordingly. This is the radius. Okay, so if we know that point blah blah blah, we want to know the value of tan theta. Well, all we have right now are things that tell us cos theta. Sorry, sine theta. No, cos theta. My bad. Sorry. I'm going to stop confusing you guys. So cos of theta, which is opposite over hypotenuse. Obviously, opposite is y, right? So right now we have y over r because we've got 13 and we've got the y value. Okay, well, that's cool and all. We like that. Ow. So if we're going to go ahead and do that, we can say, well, this is, oh, this stupid pen drives me crazy. It happens at least once every hour where I click the wrong thing and it just goes crazy. So, okay, we've got -5 over 13. Awesome. So we have cos of theta. Can we solve for sine of theta? Well, yeah, we absolutely can, because we know that we could just solve for this theta and get that as a reference angle and go from there. Well, another thing that's important to note is that the fact that this is negative tells us that it's in the negative area here, and it's either in the top quadrant or the bottom quadrant. We don't know necessarily yet. So let's try to solve for theta in particular. So theta equals cos theta to the -1. And I'm just going to make this positive for the sake of this. So I hope that makes sense to you guys as to how I'm able to make it positive. It's really just because I'm using a reference angle, okay? So let me just make sure my calculator is in the right degrees. So let me just double check cos of 45. Good. Okay. So 5 divided by 13 cos to -1. So sorry guys, just plugging this into my calculator real quick to make sure I'm getting you the right answer. So we've got 67.38. We're just going to call that 67 degrees. Okay guys, so let's take a look here and solve. Just give me 1 second. Now, this is one way to do it. Okay, you can solve for the angle and then work backwards and then solve for y. There is also another way to do it with literally just the Pythagorean theorem. This should be r. X squared plus y squared. And we've got 13 squared equals x squared plus -5 squared. And we get 169 equals x squared plus 25, and x squared equals 144, and the square root of that is 12. So we have x. And now, since we know that tan is opposite over adjacent, and that y is opposite and x is adjacent, we can go ahead and solve for tan, which is going to be y over x. And we're going to get -5 and 12. And we don't need to worry about changing the sign, because obviously if the sign was going to be anything else, it would have been that. So we have tan of theta, okay? And we know what quadrant this is in. How do we know what quadrant this is in? Because if we look here and we look at our different quadrants, we know that cos, sine, right? Well, we also know that the tan is sine over cos. because I'm pretty sure that is what the identity for tan is. Just give me 1 second, I have it right here. Yeah, it's sine over cos. So sine of x over cos of x, or sine of theta over cos of theta. And so that means that if tan is negative, that means that at least one of each has to be negative. And in this case, we know that the sine here is negative. So that means that it would have to be somewhere down here. And we know that the cos is positive, so we know that this angle is somewhere in here. Somewhere in here. We don't know exactly where. It's approximately 67 degrees from the x-axis, realistically, but it's approximately somewhere in there. Okay? So altogether, this angle would be like that. Okay, guys, so I hope that that makes sense. If you have any questions about that, we can definitely go over it. Let's take a look at something similar but a little bit different. So again, when you're getting these types of questions, I'm just going to refer back to the last slide, and over here, I'll draw your attention over here quickly. Again, it's not about memorizing the letters and where the letters are. It's really just about understanding why we are using these letters in place of this. I do remember my own self in grade 11 just being super confused by this. And now that I've tutored it a bunch of times, I'm like, oh dang, if I had just like asked 2 questions of my teacher, I would have understood it. It's not as crazy as we think it is, and I think a lot of times we are encouraged to memorize when in fact memorization is not the way to go. Okay, guys? So let's take a look at a different problem. How many minutes do we have left? 8 minutes. Okay. So what is the value of tan to the negative 1? Let's see here. I just want to find us a question that will actually help us in this case. So this is a question that I see a lot on exams and tests. So if cos of theta is 0.267 and 0 degrees is less than theta and theta is less than 90 degrees, what is the value of my guy theta? Of theta. So we can very easily solve that. We've got the cos value here. Make sure that your calculator is in degree mode. So go ahead and check that. And then you go theta equals cos to the negative 1, 0.267. This is grade 10 stuff, this part here. And then we can go ahead and get that angle. So cos to the negative 1, 0.267 is 74.5 degrees. And we've got 75 degrees as a rounded. Now, what if they said to us cos of theta, so this is one question. Here's a follow-up question, and the likelihood is that you'll actually get the follow-up question more so in what we are looking for. So, for example, you would get a question like cos of theta is negative 0.267. And the possibility is that it's an angle anywhere between 0 and 360 degrees. So theta is between, okay? Now you'll get questions like this all the time on tests. And again, I know you guys are probably not going to be writing tests, but this is really important stuff that you do need to understand, okay? So let's talk about what we are referring to here. So if we look at our Cartesian plane over here on the left, when cos of theta is positive, we know that that means that cos of theta is relating to an angle either here or here, okay? Because this is where cos is positive, because x is positive here. But when cos of theta is negative, that means that this angle could be either here or it could be here. And actually, in situations where they're not specifying what sine is, the likelihood is that you're going to have to answer for both of these quadrants. You're going to have to give an answer for what the angle could be in this quadrant, or what the angle could be in this quadrant. Alrighty, guys. So first things first, since we know that our angle, our reference angle, is 75 degrees, well then I'm pretty much already on my way to getting the answer here, okay? So 2 ways I can solve for it. First, I want to solve in this quadrant. So I'm going to say, well, what's 180 minus 75 degrees? And that is going to be 105. What am I talking about here? And then we also are going to have 180 plus 75 degrees. Why am I using 180? Because again, we use reference angles in reference to the x-axis. Okay, guys, that's really important to remember. So this is going to be 255 degrees. Alrighty. So these are both answers that are correct for this particular situation, for this particular question. Okay, guys, I hope that that makes sense. Like I always say, if it doesn't make sense, just leave a question and we're happy to answer that. Okay, guys, we are going to do, let's see here, probably one more question and then it's time to wrap up. So let's take a look. Let's try something along the lines of something kind of like what we just did, but again, more so what you would see on a test. So where theta is between 0 and 360 degrees, identify the angle that has the same sine ratio as 330 degrees. Cool. We can definitely do this. We have all the knowledge necessary to complete this task, you guys. We're killing it. Okay, so let's take a look. X, Y. Okay, 330 degrees. Well, that is right here. Because it's about 30 degrees. Wow, this is why I use the arrows usually. It's about 30 degrees off of 360, right? So this is 330. Alrighty, guys. Well, okay. Let's discuss how we're going to solve this. First and foremost, what's our reference angle? Well, this is negative 30 actually. So our reference angle is going to be positive 30. Killing it. Alrighty, guys. So we've got positive 30 as our reference angle. What is the sine ratio for positive 30? Well, we know that to be 1/2. So sine of 30 is 1/2. Well, identify the theta that has the same sine ratio as 330. Okay, that's fine. We know that as long as we're talking about the same sine ratio in terms of its absolute value, right, then that's no problem. We can absolutely solve for that. And we know that as long as we're referring to the absolute value, then that makes sense. If we were not referring to the absolute value, then this does not make sense because this sine value is going to be negative. Whereas this sine value for positive 30 is going to be positive because, again, of the position on the y-axis. Okay, guys, so that's our final question for today. I thank you guys for tuning in. I appreciate everybody taking time out of their day to continue learning math even while schools are closed. You guys are awesome, and I hope to see you again next week. And if you have any questions in the meantime, feel free to email them to us. You can go to our website. You'll see it here at the bottom, scholarlyelite.com, and you can send us a request on there, and we can answer your questions next week. But I hope this was helpful for you guys, and hope you have a wonderful week until next time, okay? Have a good one, and we'll talk soon. Thank you, guys. And then we're just going to have a minute until the grade 12's class starts while I get everything in order quickly. Okay, if you are just tuning into our grade 12 class, welcome and thank you for joining us. We are here at freemathhelp.ca, as you know, probably how you got here. And I am Arlinda. I am the CEO at Scholarly Elite Tutoring, and I have been a math tutor for many years, although I haven't tutored in the past year or so, just because things have gotten busy at Scholarly Elite. But we are here to help you guys as best as we can, and if you do have any questions that you want to submit to the chat, you're more than welcome to. If you don't have any questions, and if there's no questions in the chat, what I do each week is I actually go ahead and teach a lesson, and it's always a lesson that pertains to the grade 12 course. In this case, the grade 12 course is in fact the MHF4U, which is the Advanced Functions grade 12. So we're just gonna wait one more minute to see if anyone else joins, and then we're gonna get started. Okay, guys? Thank you. So the thing we're going to be talking about this week is trigonometry, and there's a couple different areas of trigonometry that we are going to focus on. I know that one area that a lot of people tend to struggle with are trig identities, and so we are going to do some of that as well. But if you guys have, like I said, if you have any questions that pertain to anything else, feel free to ask in the comments. Okay, guys? So, like I said, we're going to be talking about trigonometry today and a couple different aspects in the trigonometry world. But the thing about trigonometry is that it's a very vast subject and there's many, many aspects involved. So we're likely not going to complete an entire trigonometry unit just in this one day. So it is important to remember that, you know, if you do want to have a deeper, in-depth understanding of it, come back again next week. We're going to continue on. Each week we're going to be learning some stuff and just really helping you guys understand all the stuff that you need to know. So first and foremost, when we're talking about trigonometry, we are realistically always talking about the unit circle. But first, what I'd like to do are some examples on the actual trig identities. So I think that in the grade 12 year, you guys really, really do put a heavy focus on trig identities, and it's important that you understand them and how we solve them. Okay, guys? So before we do that, though, I do want to go over converting from degrees to radians, because that is part of this course as well. So if we think about our unit circle and we know that the unit circle is in existence kind of on the Cartesian plane, and the Cartesian plane and the unit circle have a 360-degree quality to them. Pretend that that's a perfect circle. So if you think about it, from here to here it's 180, and then from here to here it's 360 altogether for the whole thing, right? Now, keep in mind that when we're talking about the unit circle, we usually start by learning it in degrees. So we know that, you know, we start at 0, we go to 90 degrees, we go to 180, and then we go to 270 here, and then 360 all the way around. Well, obviously, when we get into the grade 12 year, things get a little bit more complicated, and we actually are expected to understand these in radians. Now, radians are just another way of describing angles, and the reason that a lot of people end up liking radians better is because once you get a hang of them, they're actually more logical. They make more sense. So from 0 to here is pi by 2. From 0 to here, from 0 to 180 is pi. Here we've got 3 pi by 2 in place of 270, and all the way back to 2 pi. Okay, guys, so when we're talking about radians and converting it to degrees or vice versa, we have pi radians equals 180 degrees, and 2 pi radians, and remember that radians is an SI unit, is 360 degrees. okay? So the way that we can kind of break this down, if we're thinking about 1 radian as being equal to 180 degrees, it's actually really easy to get our answer when necessary. So I'm going to show you guys what I'm talking about. So say we have an angle, and we know that the angle is the length of the arc divided by radians. And if you guys have not gone over this in class, I highly recommend writing this stuff down. It is going to help you. Okay, this is a really important one. So let's take a look here. So if we have pi radians, and we know that it equals 180 degrees, well then we can just use that to solve. Okay, so I'm going to show you what I'm talking about. Let's make some space here. So if I know that I want to convert 90 degrees to radians, and this is a question that you might get on an exam, on your tests, and again, we don't know if you guys are going to go back to school this semester, but if you are taking this course and then planning on taking calculus in the future, it is important to understand this concept, okay? So if I have 90 degrees, I'm going to multiply it by pi over 180 degrees. And for anyone who's taking chemistry, this is also how we cancel stuff out in chemistry. Okay, so we have 90 degrees. So realistically, all we can be left with is the radians answer. So in any conversion, the unit that we want to solve for is in the numerator. Okay, guys? So this really leaves us with 1 over 2 pi. And that means that we have our answer, which is pi by 2. 90 degrees is pi by 2 radians. Okay? Let's do another example. Now, before we go on to another example, I want to explain this part here, why it is the way it is. Okay? So when we're converting from degrees to radians, again, remember that pi radians is equal to 180 degrees. Well, that means that if I want to be left with pi, I have to divide off 180 to be left with just pi. Okay, so let's say I'm asked to convert 150 degrees to radians. Well, that's definitely doable. We can now go ahead and say, okay, well, 150 degrees times this conversion. So it'll look like that. And the whole point is, again, that we're canceling out degrees. That's really what we're trying to do here, right, guys? So what we're left with is when we get this all multiplied, it looks like that. And the real kicker here is that we can reduce that, obviously, and take it as 5 over 6. Okay? So this is not the most difficult part of this unit, but it is a part where if you don't understand this, it's going to make your life a lot more difficult. And on top of that, it's kind of what the rest of this unit is predicated on, is you understanding this conversion rate so that you can apply it in a way that's actually helpful for you. So I really highly recommend you practice this. We're going to do one practice question now where we convert from radians to degrees, because you do get that sometimes. And we can definitely go from there. So let's do the opposite and convert from radians to degrees. Well, no problem there. Convert to degrees. Well, we've got 5 pi over 3. And I want to convert to degrees, so I'm going to, again, remember that whatever I want the unit to be in the end needs to go in the numerator, because the denominator is used to cancel out the unit that I do have. So I know that for every 180 degrees, I have 1 pi radian. So I'm going to use this to cancel stuff out. Okay, so we've got right here, we're taking a look, and we've got this. So we've got 5 times 180, and we can even leave the pi in the beginning, 3 pi. So these pi's cancel out. okay? And then we've got the answer, which is going to be 300 degrees. Alrighty, so if anyone has questions about that, feel free to leave them there. And I will gladly answer those for you. But hopefully that makes a little bit of sense for you guys. So this is a really important part of this unit. We're going to come back to doing stuff like this later, but today I really wanted to focus on understanding some tricks for solving trig identities. Okay, guys? So let's do some trig identities and not want to cry. Okay, guys. So 1 minus sine squared theta times cos squared theta. So when we have questions like this, there are a couple different things that we want to focus on and that we want to solve. Now, from grade 11, we're used to solving trig identities as equalities and showing that the answer on one side is equal to the answer on the other side. Things change a little bit in this scenario. Sometimes you'll get questions like this and they're asked to simplify them, which is not that difficult, I promise. I'm going to show you guys how we can do that and how we can solve for what we need to solve, okay? So in this case, if we remember, we have a trig identity that says sine squared theta plus cos squared of theta equals 1. And if we have a decent understanding of the unit circle, that makes sense to us, okay? Now, the reason that this is the case is because the radius of the unit circle, the unit circle has a radius of 1, yada, yada, yada. It's a long story. But point of the story is that this is an absolutely must memorize trig identity that you guys should know, okay? So keeping this in mind, this now means that cos of squared of theta is 1 minus sine squared of theta, if we were just to rearrange that. And then sine squared of theta equals 1 minus cos squared of theta. Okay, this is kind of an addendum to this stuff here. Alrighty, so in this case, we can actually just take this 1 minus sine squared theta and turn it into this. Tricks for trig. Yes, hi. Okay, guys, so now what we're going to do here is take a look. And when solving equations like this, we want to simplify as much as possible. So again, we recall this here, and we're going to apply that. So now let's do that replacing, and we did. And this equals cos to the 4 theta. The reason I showed you guys this example to begin with is because in situations like this, it's very important to understand that the rules of exponent laws apply. And this is where so many people that I've tutored get confused because they think to themselves, okay, well, I'm at this point here. What do I do now? Simple enough. It's the same thing as saying x squared times x squared, right? Those are going to be added and we're going to get that. So that's how we get this answer, okay? This, another way of saying this is cos of theta times cos of theta times cos of theta times cos of theta. Okay, I don't want to go into this too much because I understand that you guys are in grade 12 and you do get this kind of stuff, but I like to preface this lesson with this concept because once you understand that the laws of exponents still apply and that you don't have some special rules, you really make your life a lot easier for yourself. Okay, guys? So let's take a look at some more intense trig identities. And if we have time, we're going to get into all of the various fun and crazy ways that trig identities come up in grade 12. But just give me 1 second to grab the stuff here. So we're going to start off with, now, like I said earlier, a lot of times in grade 11 when we're learning trig identities, we understand that we're trying to get the two sides to equal one another, and sometimes we have to break both sides down, sometimes we have to break one side down. What's really happening in grade 12 is that not only are they expecting you to understand the breakdown of each thing, but they also want you to solve for them oftentimes, okay? Now, let's take a look at a question like this. 1 minus cos squared theta, because it does kind of go based on what we were just talking about. We have cosecant squared of theta equals 1. So we know that cosecant of theta is equal to 1 over sine of theta. And secant theta is equal to 1 over cos, which I've always thought it's dumb how these letters are the opposite. But anyways, you know, nobody asked me. They just went ahead and created this crazy rule. So there's that. So, okay, guys, like I was just saying, you know, we know that 1 minus cos squared of theta, we can also call it something else, and we will in a quick second. But before we get started with that, we're going to do this, okay? Every single time you get a question like this, my first suggestion is just simplify, 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 okay? So if I know that cosecant theta is 1 over sine of theta, then this also means this. Okay, guys? So this means this. Sorry, I'm going to cut to this part in a second. Now, so I've now simplified the cosecant squared, and I'm going to come onto this side and figure this stuff out. So let's go ahead and do that. The 1 I'm going to leave as it is right now. But I'm going to convert this into that identity we were looking at earlier, which is the cos plus the sine equals 1, and then just rearranging that. Okay, so let's take a look at what all of this comes to. So I'm keeping this 1 from here, this one, and I'm going to change this now into 1 minus sine squared theta. Alrighty, guys. So again, typically these types of questions, my number one trick for you, first and foremost, is that whenever they've given you something that you can write in a different way that's more simplified, typically the more simplified version is going to be the one that you need. So for example, we had cosecant squared, we changed that into 1 over sine theta squared. Here we had the cosine squared, I changed that into 1 minus sine squared theta. Okay, let's go ahead and solve now. Well, here, when I multiply this all out, this becomes 1 minus 1 plus sine squared theta. And I know that 1 minus 1 is going to be 0, so I'm really left with sine squared theta times 1 over sine squared theta. And I know that when I multiply these together, because this is numerators, technically this is over the number 1 times denominators, we've got sine squared theta over sine squared theta, and we get the number 1, because obviously anything divided by itself is going to be 1. Okay, so this is a perfect example of my first trick, which is ultimately the whole point of these is to simplify, keep that in mind, and don't try to jump 10 steps ahead. Sometimes these require a little bit of trial and error, and that should not get you down. If you didn't get it right the first time, that's fine. Go back and try it again. It's not the end of the world. Even those of us who do these who have done these all the time as tutors or as teachers, when we're given a new question like this, sometimes it does take a little bit of trial and error because you have to make certain assumptions at each point, right? And that will help you. Another thing is that I really highly recommend is trying to get everything in terms of the same identities. So try and get it all in terms of sine. Try and get it all in terms of cos. Keep them as streamlined as humanly possible. Okay, guys? So we're going to go ahead and erase this one and try something else here. McDonald's, please don't come after me. I just like your theme song. Alrighty, guys. So let's take a look here. Let's try another example. Very similar to this one in a way. Because it's going to illustrate the point that I was just making, and we're going to go through this one kind of quickly because it is very similar, but I did want to show it to you guys just so that you can get an idea of what I was talking about just now, about streamlining these and trying to get them all in the same trig identity overall, okay? So secant squared, we know from here that it's 1 over cos of theta, and in this case, because it's squared, I have cos squared theta. Here, I'm going to change this 1 minus sine squared theta to say, sorry, just one second. Yeah, so here I'm going to change this to 1 minus cos squared theta. This is a hugely popular trick that you're going to see all the time. Okay, guys? So whenever you see sine squared theta or cos squared theta, and if you can use that to create a similar or the same trig ratio on the same side, that's important. Okay, guys? So let's go ahead now. Keep that part the way it is. Here, these ones are going to cancel out, but we're going to write that together in a second. And it's the same concept that we just learned, but again, I just wanted to illustrate to you that what I was really doing and what I often recommend for my students to do is to get everything in terms of one type of trig ratio. So here I made everything in terms of cos. Okay, guys? Okay, so let's move on to something a little bit more complex, because I know that these get real crazy and that teachers like to give you guys very, very intense questions in this unit. So let's do this one. Tan of theta plus secant of theta minus 1 over tan of theta minus secant of theta plus 1. And we're going to make that equal to 1 plus sine of theta. Oh, dang it. Oh my gosh. Over cos of theta. So on the left side here, as soon as I look at this and I'm seeing my tans, I automatically want to deal with that because this is a bit of a crazy looking question, but we can simplify this quite quickly. So I'm going to let you guys write this down quickly and then we're going to go ahead and do that together. Okay? I want you guys to try it out. Okay, guys, so let's try this bad boy out. So first and foremost, what I want to do here is say to myself, well, tan can automatically be broken down into sine over cos. We know that because that's a very standard trig identity, sine theta over cos of theta. Cool. So I'm going to go ahead and break down the beginning, or the top part of this first. So we've got sine of theta over cos of theta minus 1 over cos of theta minus 1. Okay, this could have been this. All over sine of theta over cos of theta. Oh, this was plus on the top. And then we've got 1 minus cos of theta minus plus 1 in this case. I'm going to work on the left side kind of exclusively for right now. So one thing that I do want to do here is to make sure that we have a common denominator all the way across. So I'm going to multiply this top part by cosine, or sorry, this 1 by cosine. So I'm going to go ahead and say sine of theta plus 1 plus cos of theta all over cos of theta. And then that's divided by sine of theta minus 1 plus cos of theta over cos of theta. Okay, guys, so now ways that we can make this easier. Number one. Oh, I was trying to erase that. Let me just get rid of this stuff here so that we have more space. Whenever I get a question like this, and remember, we're working only on the left side of this problem right now. Whenever I get a question like this, I find it much easier to just write this out like this. Sine of theta plus cos of theta plus 1 over cos of theta divided by sine of theta minus 1 plus cos of theta. And then we've got cos of theta. Now, what's really going to happen here is that because it's a division of fractions, it's actually going to flip the sides and it's going to become a multiplication. So we're just going to write it like this. Cos of theta, and we've got sine theta plus cos theta minus 1. These cancel. And we're left here with sine of theta plus cos of theta plus 1 over sine of theta plus cos of theta minus 1. Okay, so now we're going to kind of move this over and up just so that it makes a little bit more sense. So I hope everyone is doing okay and following along. Okay, so here now we can go ahead and say to ourselves, well, this is going to be sine of theta plus cos of theta plus sine squared theta plus cos squared theta. And this is going to be sine of theta plus cos of theta minus sine squared theta plus cos squared theta. And then ultimately that just becomes sine theta plus, sine squared theta plus sine of theta plus cos squared theta plus cos of theta over sine theta plus cos theta minus sine squared theta minus cos squared theta. Okay, so I know that this all looks a little bit crazy right now, guys, but what we are trying to do is simplify this as much as possible. So wherever I have a lot of sine squared thetas, what I'm going to do is basically just convert them if I can. So here, let me just erase this part. And I hope you, if you've been following along, I hope you're writing this down just because it's a little bit hard for us to use all of this one screen. Okay, so here what I'm going to do, because I know that in this top part, this is left with just the sine, right? So I'm going to say sine squared theta plus sine of theta plus, and I'm going to convert this cos squared theta into 1 minus sine squared theta plus cos of theta. And then here, I'm going to get sine of theta plus cos of theta minus sine squared theta minus 1 minus sine squared theta. So what's really going to happen now is we're going to cancel some of these bad boys out. So we've got sine squared theta is going to be eliminated. And then we've got 1 plus sine of theta plus cos of theta over 1 minus, so here these are going to cancel, so negative sine of theta, that's going to be plus, so that's going to cancel as well. And then we've got 1 plus sine of theta plus cos of theta. And then basically what we can do is factor that out, okay? Just 1 second, because I seem to be having some issues with my internet. I don't know why it keeps cutting in and out. Let's just see. Give me 1 second to try and fix my internet, you guys. Okay, you know what, you guys? I don't know why my internet is acting like this. So hopefully you guys can hear me. My internet is acting up. If you can hear me and you're still here, I want to make sure that people who are watching can actually hear. So if you can't, we're going to wrap this up early today because I don't know what's going on with my internet. But if you are, you can set, if you are here and you can hear me or can't hear me, I don't know what's going on with my internet right now. Send an email to this email address. Let us know that you were part of this live stream, and I will personally give you half an hour of free online tutoring just to make up for it. Okay, guys? But I'm really sorry because I don't know what's going on, and I hope that, I don't even know if you can hear me or not. If you can't, I'm really sorry. Hopefully you can. But I'm just going to wrap up the live stream because I don't know why my internet is acting like this. Okay. Just going to wait another like 30 seconds and then we're going to wrap it up if I don't hear from anyone on the chat. Thank you for joining us, by the way. I'm sorry that this is going on like this. I don't know why it is. But join us next week, which at that point I'm hoping to have fixed this internet issue and we can do some more stuff. Okay, guys? Hope you guys have an awesome week. Thank you for joining. Sorry about this. I don't know what's going on with this. But like I said, if you are part of the live stream and you can hear me, then just send an email to admin@scholarlyelite.com and we'll get in touch and we'll give you free half an hour tutoring online. Okay, guys? Thank you for your understanding and I hope you have an awesome weekend. Have a good one. Happy Easter, guys.